All right. I think we can start again. Next speaker, as you can see very well, is Maxime. Please, you have the stage.
Thank you. It's a great pleasure to be here. And I would like to tell today our recent results about stars. But if you don't like stars or if you don't like variability breaking, I hope that stars are going to be like start of the game. And towards the end of the talk, I will go a bit more into controlling matrix product states and quantum space like methods for matrix product states. And hopefully, this will also may be interesting for those who are interested again in generating quasi-diabatic transformations and how to control quantum many-body systems. And let me start by acknowledging my collaborators. A lot of this stuff would be impossible without senior collaborators like Dima and Norbert, and also people who are in the group and who are pushing. And this is like where we are. So this is again suburbia, a bit more closer than here, but also beautiful from its own perspective. So stop by if you're around. And let me start with the motivation, right? Many people here are interested in universality out of equilibrium, and we sort of understand that, thermalization is default outcome, right? I take a quantum system with small degrees of, small spins, quantum degrees of freedom, right? It's interacting, there is no special symmetries. I'm expected to be here, right? Then we heard, like from some previous talks, that maybe if you impose some extra symmetries or you crank up this order to be really, really strong, maybe thermalization just goes out of the window, right? And then all states, right? All eigenstates are not thermalizing, right? And what I want to say, right, sort of my big motivation is that maybe it's not like black and white, right? Maybe it's not like there is only thermalization or only pure, integrability or localization. Maybe there is a whole spectrum, right? And I think this is now speculative, right? I don't have any measure how to measure kind of where I am, right? If you have your favorite Hamiltonian, is your favorite Hamiltonian here or there or there? But maybe this is more of a reality, right? And why may I expect so? Just because we know the lessons from a few body chaos, right? In a few body chaos, we have systems which like kicked rotor, right, which avoid thermalization because of some magic mapping to Anderson insulator. We have some systems which again are very, very, very chaotic, but also we have typical system in a quantum chaos, and a few body chaos would be in between, right? There would be mixed phase spaces, there would be complicated behavior. Maybe many body systems are similar, right? Maybe, of course, if we deal with random circuits that are like, random matrices, there is no structure left. Maybe there must be there, right? Nothing else is possible. But maybe if your favorite Hamiltonian is not a random circuit, but like Ising model, you have some more like structured Hamiltonian, right? Maybe it can have chances of being somewhere on the spectrum. So that's a motivation, right? And again, there are specific questions to ask, right? Like how to quantify this and so on. But talk, again, this is a motivation for my talk, and talk is going to be much more specific. So I'll start with actually briefly telling about one specific Hamiltonian and, this quantum many-body scars and trajectory description of them. After that, I will move towards more abstract language, hopefully motivating these questions about forecast systems and about leakage. We're going to see what it is. And finally, maybe I will touch about some strange non-Hermitian models that we can get out of there. And motivation actually comes from atoms on, experiments on Rydberg atoms. We heard about some beautiful experiments earlier. This is somewhat different regime of so-called Rydberg blockade, right? And the idea is that their Hamiltonian can be written very simply, right? This is, pretty much paramagnet, but a projection is imposed that no two nearby spins can be up, right? That's again very, very simple operation. Paramagnet is a trivial non-interacting Hamiltonian. This Hamiltonian is interacting. It has a very strange Hilbert space because I throw away two up spins from the Hilbert space, right? Nearby spins cannot be in the up spin state. This model, if you like to think about it, it also can be thought as a graph, right? Edges are Hilbert, all allowed product states after this constraint is imposed, and edges means that the Hamiltonian has non-zero matrix element between them, right? This is a matrix with zeros and ones. So this is this Hamiltonian for 6 Rydberg atoms with periodic boundary condition. Now I'm showing experimental movie that is going to simulate a quench, right, on slightly bigger system. And what this quench is doing, it prepares function in a one product state. And you see, surprisingly, visually, this is apparent, this is ergodicity breaking is happening here, that there are many vertices in the graph. system starts with a product state, spreads over many of them, right? And then starts bouncing back and forth, right? So that would be the idea, right, of ergodicity, just intuitively. This is a huge Hilbert space. I start with a product state, I explore many states, and then I'm stuck there, right? I'm not supposed to be reviving and coming back here and there. So that's, again, that's the motivation. That's why I'm interested in this model as a starting point. And we can ask what's the, what's behind this kind of strange behavior. And this is, again, this quantum scarce. So the idea would be that this model has some strange eigenstates, which are non-normal. You can measure, for example, you can find the strange eigenstates by studying their overlaps or studying their wave functions. And the idea is that many other eigenstates look like they're behaving in a typical way, but these strange states are like very, very apparent. But today I want to shift gears, right? This is all eigenstates, this is all Hilbert space. Hilbert space is ridiculously complicated. It's exponentially growing, big space. Let's think about, some simple variational description, right? Because this phenomenon that I showed, this kind of movie, which looks very complicated, right? There are many, many vertices, some stuff is oscillating. If I'm just looking at my system by eyes, I'm seeing something ridiculously simple. I'm seeing oscillations between two Niel states. I have Niel state up-down, which is translationally invariant with period 2 translations. And I have a partner Niel state down-up, right? And what I see is the system keeps oscillating between two states. And these oscillations are surprising because these two states are very, very highly excited. So it's not like I have some spin wave excitation, which is near ground state. These states have zero energy densities. They live in the center of many body spectrum. And yet I have stable oscillations, right? So I can oscillate between two specific translational invariant states. And these oscillations are long-lived, right? And there is an atypicality. I can take another favorite translational invariant state, and usually I'm not going to see these oscillations, right? That's what's surprising here, is that from highly excited initial state, oscillations are long-lived, and this is not happening for every state. So now I'm going to live in dynamics picture, right? I don't want to think about eigenstates. I can talk about eigenstates a lot, but dynamics picture, it's kind of interesting, right? So how do I do dynamical description of this problem? And I would say, let's do mean field. Let's take mean field. I have only two different spins, one up, one down. All others are copies. So I need just 2 degrees of freedom, right? I need spin 1 and spin 2, right? The problem is constraint. The problem is that constraint says that no spins must be up simultaneously nearby. So I cannot do a mean field, but I can do MPS. I can do projection on a matrix product states. And you see where the magic comes from. The magic comes from a Pauli matrix sigma plus. So raising matrix sigma plus squared gives me 0. So if I'm assigning a weight of excited atom of up spin to be sigma plus, then I cannot put two ups next to each other, right? That's the magic. And this magic actually is funny because it's like a product state, but it has a bit of entanglement, right? It's now became a bond dimension 2 MPS. And how we can understand oscillations in this Rydberg model, we can project our exact quantum dynamics, we can project our Schrödinger equation onto this bond dimension 2 MPS with just 2 degrees of freedom. This projection is doable analytically and gives you a system of differential equations of first order. Actually very rich. It has a symplectic structure as a consequence of unitarity and so on. But if you wish, this is like some sort of strange mean field, a slightly improved mean field description of this Rydberg atom chain in this limit. And once you do it, you can ask, okay, this is a system of 2 variables. Let's study its phase portraits. And once you study its phase portrait, as was done by Harvard group, you discover that there is a periodic trajectory. And this periodic trajectory, not accidentally, probably connects exactly these states in experiment which oscillate between each other, right? There is a Z2 state and a shifted partner. And this periodic trajectory just goes through them. So if you wish, right, I can study eigenstates of this model and so on, but I can just do this mean field, slightly improved mean field, and I find a periodic trajectory. Yes? Mm-hmm.
Why is the angle theta the same between the two A's?
Well, this is for one side, right? So there is theta odd and theta even, or theta A and theta B. So I need just 2 angles, right? And you can ask where's the conjugate angle, but conjugate angle can be set to a certain value and will stay there. So it's a bit of simplification.
But in principle, I could still imagine a more generic structure for these 2 matrices. I mean, you have in mind an angle because you have the mean field factorized.
Yeah. No, but this is like a, this is the simplest form of MPS ansatz to project, which captures dynamics. Indeed, this is not the most generic form. So this is like sub-manifold of MPS bond dimension 2, but it does the job, right? You see that this got a trajectory, and this trajectory explained it. So now I must kind of acknowledge, right, that this projection is not exact. So this projection is very, very poor man kind of thing. I'm taking many-body system and projecting it on a manifold of very, very simple states. And there is a quality factor of this projection, so-called leakage, or you may think about it as a Lyapunov exponent. So this variational principle projects me onto tangent space, and I can quantify how much norm is discarded. And this is what is shown by color here, right? And you see that there is a magic, not only in the fact that there is a periodic trajectory, but this periodic trajectory is where the color is very light. So it means that this periodic trajectory is not too unstable with respect to kind of going outside of my variational manifold, right? And that's, again, the idea or the explanation of this phenomenon. Is there a question?
Yes, which is the other green point and the other blue point?
This is 0 state. This is a state with all atoms down. And you see that this doesn't have any trajectory to flow in this high leakage region.
The two green points and the two blue points.
So each of them has 2 copies here.
I see.
So there is like, this is equivalent to this one. So, this is really the same state.
Sorry?
Yes.
If you start like circling on the trajectory, sure, okay, you remain there. But since you are not, I suppose that you are not exactly on that. So eventually you will circle spiral toward the center and go away from it.
That's a good question. So that's why, I really say that this 2-dimensional phase space is not generic. Let's do it in 3-dimensional phase space, right? That's exactly my next slide. So what happens in a larger phase space? And I can do the same game, right? I have now 3 angles. It's the same ansatz. It's very, very restricted, very, very simple ansatz. It's more angles. Equations of motion are terribly ugly now. They're not as elegant, but I don't care because I'm going to be doing Poincare sections of them. And the moment I do Poincare sections, I see that this 3-unit cell ansatz has very, very beautiful mixed phase space. So it has big KAM type tori, which are in the center, there is a stable periodic orbits. And these tori are actually all symmetry equivalent, right? So they look different, but they all physically correspond to the same dynamics because system has a lot of symmetries, right? It's a 3 identical sites. I can flip, I can translate, and so on. So this is equivalent tori. But there is also many other smaller kind of islands. So there is many unstable trajectories. There are probably many stable trajectories in this picture. And you can ask, do all of these trajectories give experimentally revivals? And that's actually, again, very, very interesting lesson. That, for example, I can compare this trajectory, which is in the center of a torus. And this trajectory gives me new experimentally verifiable, experimentally testable initial states. It tells me that I have initially weakly entangled state. So this state is not a product state. And this weakly entangled state is going to have very, very slow entanglement growth. And it's going to be doing better than the product state, up, down, down. So I'm telling you that this is teaching me that best state for periods 3 revivals in the Rydberg chain is not up, down, down, but is the center of this KM torus. And it has a bit of entanglement. It's area low bond dimension 2 MPS state. It's not too strongly entangled, but you see that it has parametrically slower thermalization compared to this 3 product state. And now I can ask again, this has a lot of trajectories. So let's say, does this trajectory matter or no? And you see that this trajectory not mattering a lot, right? Because I'm plotting some entanglement, and you see that this trajectory very quickly reaches a lot of entanglement, right? And doesn't have interesting dynamics. So again, lesson from this variational projection is that trajectories are interesting, but not all trajectories are created equal, right? And then, let me discuss kind of a bit this object, which I call leakage. Again, this object is, in principle, it's like Lyapunov exponent, but Lyapunov exponent to extrinsic Hilbert space, right? I'm starting with a very, very constrained Hilbert space. I'm projecting my variational dynamics at each time step. And then the idea is that, this quality of projection is gamma. And gamma can be made, actually, can be calculated in thermodynamic limit. It's like norm loss per site of your MPS. And this gamma is roughly speaking at Lyapunov exponent, right? And criterion for having revivals in the system, if we, again, and this is a conjecture, right? Criterion for having revival in the system would be that this Lyapunov exponent integrated over trajectory over a period should be less or equal than 1. And again, we don't have, we have some qualitative arguments why this quantity can be bounding fidelity per site, right? This is not rigorous, but, for example, we can test it on a specific deformation of trajectory, and we see that it works, right? We are deforming our periodic trajectory by changing Hamiltonian. You see that, this is this kind of integrated Lyapunov exponent. It starts growing. and you see that this is fidelity per site, which is supposed to be bounded. You see that this bound is very, very non-tight, right? You see there is an order of magnitude difference between two quantities, but you see that again, this bound looks somewhat trustworthy, right? So the idea would be that this generalizes criterion from a normal scars, right? If you have a scars in a classical billiards, there would be criterion that lambda, Lyapunov exponent times the period, must be less or equal than 1. Here it's somewhat similar criterion, but this Lyapunov exponent is not Lyapunov exponent inside the manifold, because manifold is very, very small. It's a Lyapunov exponent with respect to going away, right? Going to bigger bond dimensions or growing more correlations that are not in my ansatz. Yes.
So if you continue to increase your parameterization of
yes
of the state, I mean, classically, you adding more and more degrees of freedom,
yes,
and these stable islands don't start to destabilize.
I think yes, there is a folklore. My understanding is there is a folklore, right? That in the many-body system, in the classical system, you don't have a stable islands, but I'm not sure it has been really understood very well, right? So yes, indeed, you're right, right? That people think that as you increase number of degrees of freedom, stable islands should go away and so on. But also what's important that here, like I'm trying to argue that this, if I'm in an island or I'm not in an island, is not so important. What is important is this integrated Lyapunov exponent. And this is extrinsic. This is not apparent from the figure, right? So this quantity must be low. And if this quantity is low, then I'm getting decent revivals, right? But now I say that I don't understand when this quantity is low, right? I'm saying that this is a quantity extrinsic to my, somewhat extrinsic to my manifold. I don't know when I have low leakage trajectories, when I don't have low leakage trajectories. And that's the motivation for a second part of my talk, right? That's the idea that, okay, if I don't know kind of when this quantity is small, when this quantity is large, let me make it small. And this motivates a following somewhat strange problem, but maybe this problem, you know, hopefully you see that this problem is motivated. So imagine you give me a trajectory in a space of matrix product states, and you tell me that in my experiment, I have some operators A1, A2, A3, and I have couplings in front of them, and I control these couplings. And you ask, what are the best value of these couplings to drive my system on this entangled trajectory, right? This is, in principle, if you wish, this is inverting time-dependent variational principle. In time-dependent variational principle, I have a fixed Hamiltonian, and I'm asking, what's the best projection here? I'm doing opposite thing. I'm saying, oh, this is my projection. I want to go here. How do I do it? And there is one answer, of course, for matrix product state. It is so-called quasi-diabatic continuation. But it's complicated, right? Because for that, I need, for every point of my MPS manifold, I need to find the parent Hamiltonian. For that parent Hamiltonian, I need to do filter function and evolution in some pseudo time and so on. So this is like, you know, this is nice as a tool for mathematical proofs, but this is complicated. So what we've been doing, we've been solving this problem recently in more purely tensor network time terms, right? We say that we don't care about parent Hamiltonians of my MPS. How do we solve this problem? Again, how given an entangled trajectory finds the best values of time-dependent couplings that generate this dynamics variation, right? So it generates the dynamics as good as possible. And now let me tell maybe how it is related to scars, right? Because it's not so obvious. So it is related to scars because imagine I solve this problem perfectly, right? Imagine I found a generator of states over my periodic trajectory. Then this A of S, if it's a normal reasonable operator, I can view it as a Fouquet model, right? It's a Fouquet model with periodic time-dependent Hamiltonian. But this Fouquet model is generally would be expected to thermalize to infinite temperature, right? The idea would be that all eigenstates of this Fouquet model are strongly entangled, very, very not featureless states. But just by construction, because this A of S returns an MPS state to an MPS state, this Fouquet model has an MPS eigenstate. So I'm constructing you a model, which is again believed to be thermalizing, and yet it has area law exact eigenstate, right? So you see, this starts looking again like scars, that this model would have one atypical state, which kind of comes back. And if I have other states, right, these other states don't come back, right? So if I succeed in this construction, I can make scars. I can have Fouquet models with scars starting from any periodic trajectory that, you know, you give me. I don't promise it's going to be simple model, but I can achieve it, right? So we solve this problem first variationally, and variationally it's a kindergarten level kind of calculus, because variationally you see that you are doing TDVP. you're minimizing leakage or minimizing discrepancy, but in TDVP, you had to minimize it over direction and tangent space, and it's a complicated object. Now I'm minimizing it over coefficients of my operators. So it's a quadratic problem. Right? If it's a quadratic problem, everybody knows how to solve quadratic problems. So it's easily and efficiently solvable in a variational way. And let's just give a proof of principle. Let's make scars from Ising model. Right? I take my transferred longitudinal field Ising model with couplings which are all of the same order. So it's a chaotic model. I find periodic trajectory in this system over an MPS, over matrix product states. And now I construct optimal coefficient C's, right? To go on this periodic trajectory with as little leakage as possible. So from constant Hamiltonianizing model, I get Fouquet-Ising model. And couplings, look like something, right? They don't, this is dashed lines are initial values of our couplings. Now couplings are time dependent. I can have just these three couplings being time dependent. I can add the fourth term, which would be like a next order kind of contradiabatic term. So this is the answer of this minimization. But now question, what does it do to, let's say, my entanglement?
Sorry, just one question.
Yes.
The fact that you are minimizing the leakage doesn't mean that the leakage is small, right? I mean,
yes, this is non-universal, right? You are totally right. And let me show you that. So this is exactly done for the sizing model. And I'm minimizing, so this is entanglement dynamics in a proper time constant generator. And you see that it's thermalizing, right? You see that I found a periodic trajectory that would be doing like something like this. And Ising model doesn't follow it much. It follows it for like time order half and then shoots up to the sky. Now I optimized over constants, right? I optimized over these three time dependent constants. And you see that I'm following this periodic trajectory a lot better. You see that my entanglement is now not growing as fast and has a sign of oscillations. But you're right, that this minimum is not guaranteed to be low. So I add one more variational parameter, and with one more variational parameter, I nearly killed entanglement growth, right? You see that now entanglement is almost not growing. But this is totally not universal. I'm not guaranteeing that the answers that I find is going to be very good. And now we can check that this also has strange Fouquet eigenstates, right? Now I can study this Fouquet operator, right? And you see that this Fouquet operator, this is again exact generalization. You see that most of the states are highly entangled, and then it has some strange low entangled states, and they're not protected by any gap, right? It would be crazy to expect a gap in a Fouquet system, but you see that there is like generic low entangled eigenstates in this construction, and it's very fragile, right? So the moment if I deform this operator, right? If I don't use these proper couplings that I came up with, right? If I deform some of these time dependencies, then this will fall apart, right? These states will go away, and it's going to be more like normalizing Fouquet. Yes?
That is optimization was done for some initial state.
It was done for some trajectory. It was done for some trajectory. I can explain more details maybe later how I get this trajectory, but it should work for any trajectory. Trajectory must be an injective MPS, and then it should work.
You also do it for one.
No, this optimization is done in thermodynamic limit. It's done with IMPS, so system size there is irrelevant. Obviously, to do Fouquet checks, I have specific system size just to construct Fouquet operator. But trajectory and all this optimization is like IMPS, infinite MPS. Okay, so now maybe in the last 5 minutes, I want to discuss exact construction, right? Right now it was variational, and we don't know how low is this leakage going to be. We have no guarantees. We can do exact constructions, and exact construction is actually very kind of also simple. I mean, maybe you learn something about MPS today, right, from this. So I need to solve this local problem. I have IMPS, the standard M. I insert derivative here, and I want to generate this derivative by, let's say, local two-body operator. How do I do it? Turns out that MPS has a magic, right? There is a so-called pseudo-inverse operator, which acts a bit like this DNA CRISPR, right? There is an operator that can cut out a part of your MPS and insert a new part. This pseudo-inverse exists as soon as the range of my operator is bigger than chi-squared. And this pseudo-inverse does following, right? I apply my pseudo-inverse and it opens this legs. Now it's trivial to construct this operator, right? This operator A that satisfies this condition is my pseudo-inverse sandwiched with my derivative, right? Because this pseudo-inverse cuts out my MPS, it cuts a hole, and this dude, right, just puts back derivative. So I constructed it, great. Should I go home? No, because this is non-Hermitian, right? It's obviously non-Hermitian because if I conjugate it, I need to flip it, and you see that this and this have no reason to be Hermitian conjugates of each other, right? So what do I do? And again, here, like it was very helpful collaboration with Norbert Schuh. we can do very, very naive thing. If A is non-Hermitian, A plus A dagger is Hermitian, right? It's an obvious statement, but A dagger screws up this job, right? A was constructed to do the perfect job of driving me on a trajectory. I did A plus A dagger, so I screwed it up. How bad do they screw up? And it turns out that you can bound how badly you screwed it up in a range. So the idea is that if I increase range of my I and increase range of this operator, the precision with which it's driving me is going better, is going to zero exponential. So the idea is that I don't have a local Hermitian operator, but if I allow my range to blow up, I'm having sequence of Hermitian operators that in thermodynamic limit do this job perfectly. Right, and that's again, you can check it also numerically. You can see, for example, this is again fidelity after one period, right? And you see that as I increase the range of my operators, I'm doing it better and better. But then since it's not perfect, at some system size, this thing just goes down, right? That, strictly speaking, I need, all range operator, right? Do it perfectly. On one hand side, on the other hand side, it means that at least theoretically, right, for any injective MPS trajectory, there is a quasi-local, and quasi-local is not obvious from this construction. So quasi-local, this is something that we have to conjecture Fouquet model with an exact MPS eigenstate, right? So that's where we came to. So I'm gonna skip non-Hermitian part, and I'm just gonna, kind of come up with my conclusions, right? That I first discussed that maybe interesting way of thinking about scars is thinking about low leakage trajectories of my dynamics after projection on some ansatz that I think is interesting if this ansatz includes some entanglement, right? Includes some correlations. And then I used it to first, get scars in Ising model, right? So if you have Ising model, but you can time change couplings, you can have scar-like behavior. And then I try to argue that actually you can have exact scars, right? You can have models which are quasi-local, and they're going to have perfect scars with fidelity 1. Again, the price to pay for it is that the operator is going to be quasi-local, right? And I had to skip this part about finite range non-Hermitian stuff. It's not a big deal. And sort of, again, it's like, let me just stop with the same question that if there are many, many models, Fouquet models with scars, right? Again, maybe this is some basis that things are not black and white, right? That I have now classes of models which are time dependent, which are guaranteed to have exact non-terminal at least one non-terminal eigenstate in their spectrum, right? So again, that's maybe some support to this picture that stuff is not black and white, and even without this order, we have interesting behavior and not necessarily plain vanilla thermalizations that runs, ballistically very, very fast. So stop here. That's perfect.
Amazing. Yeah.
Nice. How does it scale with the bond dimension? I mean, can you interpret? This operator was this Fouquet operator that has the eigenstate, the MPS, and
yes,
that eigenstate. Can you build it for any bond dimension? And
yeah, I mean, again, the price is we didn't explore it in the bond dimension because the price, right? This construction starts working when 2 to the power range, that's a spin half system, right? When you're injective, right? You must be injective. So if your bond dimension is 3, you just need longer range operators to start with, right? But so again, so that's something we didn't explore. Sort of, I think again, like bond dimension is an axis. We did everything for bond dimension 2 just because it's like simplest non-trivial bond dimension. It should work for any other bond dimension. Again, the question is, of course, interesting question is this should get somehow beastier and beastier and more unstable and more unstable. And yeah, that's an interesting.
Can this interpolate between quantum scar to thermalization?
Exactly. No, that's an interesting question. Again, we haven't had yet time to study this construction. But again, I think this is generally very, very well known object in a tensor network thing. But I think generally I don't understand much about the properties of this object, right? Because it can be explicitly constructed as an inverse of transfer matrix in a vertical direction. Thereby, it knows about entanglement spectrum and so on. So it's a very, very natural object. But I think it's not very much loved in a MPS community, right?
Can you say something more about this non-Hermitian?
About this non-Hermitian stuff, I mean, it's what I find the most strange about non-Hermitian is that it is exact at a finite range. So if I have MPS bond dimension 2, I can perfectly translate one bond dimension 2 MPS into another if you allow me range 2 non-Hermitian operators. right? That I find somewhat ridiculous, right? That again, only finite regional Hermitian operators are sufficient for generic injective MPS transformations. We are doing a bit more, kind of trying to understand a bit more of its properties. Looks like it can have more properties. Look like it may have something like a PT symmetry on top of it imposed. So again, but that's a work in progress. So.
Is that the last question?
Yeah, related, but you cannot interpret it as some sort of dissipative.
Not so easily, right? Not so easily. Just some generic non-Hermitian 2x2 beast with, you know, if you expand it over powers, it has imaginary coefficients. And yeah, maybe sometimes it's lost, sometimes it's gain, and there are many of them present. And sort of, so yeah, if you can interpret it as somewhat more physical, that would be interesting. But so far, I didn't think about really like physical interpretation.
Thank you so much, Maxime. It was a great talk.